Okay, so now we're going to shift gears a little bit, and now we're going to discuss how to find the flow rate through an arbitrary surface. And in this class, especially in the next chapter, we will often need to determine the flow rate through an arbitrary surface. So, for example, I could have a pipe here that has some velocity profile in that pipe, and I could have this sort of cutting plane here, and I might want to ask, what is the net mass flow rate through this orange surface here? Okay, and this is useful to determine the mass flow rate, m dot, which you guys used quite a bit in thermo. The volumetric flow rate. I tend to use the notation of V dot for that, but a lot of the fluids books use Q. I prefer V dot for the volumetric flow rate because when you guys take heat transfer, you will be dealing with volumetric flow rates, and also you'll be dealing with heat, which is Q, and volumetric flow rate, which is Q. So something has to give. So the volumetric flow rate in those classes is typically V dot, and I will adopt that notation. But in your textbook, they use Q. Please do not be confused by that. And then also you might want to know, like not only the net energy or the net enthalpy passing through the surface, but what's the net momentum, what's the net entropy, energy, etc. Okay, and so how do we determine these? And so first, let's just consider a small patch, dA, and that's given by this surface here. And the surface has some normal n hat right there, and we have the fluid velocity flowing. We have the fluid velocity flowing at some velocity v, and we have and along with the fluid, it's carrying its density, some enthalpy, entropy, etc. So how do we determine the net flow rate of density, entropy, enthalpy, energy, etc. through this small differential patch, dA? Well, let's go back to what you guys did in thermo for m dot. So first, let's consider mass. That's intuitively the easiest one to deal with. So in thermo, you guys know that from your class, you guys quite often use that m dot equals density times the velocity times an area. And so in thermodynamics, you often dealt with control volumes that were very simple in shape, and you implicitly assumed that the velocity was exactly normal to the surface, and it was the same everywhere on that surface. And so you know from your thermo that m dot is just the velocity of the fluid times the density times the cross-sectional area of the surface here. Okay, now we have some wrinkles here. First, we can go back up to here. What if there is a velocity profile? So basically, what if the velocity is going very slow here, and it's going faster over here? How do we deal with that case? Or what is also very common is this is sort of intuitive because the direction of the velocity vector and the normal vector of the area are perfectly aligned. What do we do if they're not perfectly aligned? So what do we do if the velocity fluid, or if the fluid velocity is not exactly normal to the surface? Okay, so let's just consider another case here where n hat again points out, but now v is going up at some angle. What is m dot? What is the net mass flow rate through? In this case, what is m dot in this case here? Okay, so how do we determine that? Well, first we need to think that m dot is going through this surface. So only, and so if you think of that, the density of if you think of that the mass is being carried is being carried with the fluid in the direction of the fluid, or you could consider a small fluid element here, and that is traveling through the surface. So so basically, only so if the particle was going straight up, you would have no mass crossing through the surface, none, because they're going straight up. Now, if it's going over at some angle, then you're going to start to have you're going to start to have mass cross that surface. So this is implying that this velocity vector here, we should break it into normal and tangential components. Okay, so let's break V into normal and tangential components like this. So we have our surface here. We have n hat pointing in this direction, and we have the velocity vector pointing up and to the right. Oops, always do that. And then, so we find the component of the velocity that is in the direction of n hat, and then we also know the tangential velocity. Well, as I argued, if this fluid particle is going straight up, its mass is not crossing through this surface here. So this means that the tangential component of the velocity Vt is parallel to the surface. It is not going through the surface, okay? Thus, the tangential component of the velocity cannot contribute to m dot. So that is, you could say that that m dot, based on the tangential component of the velocity, is equal to 0. Okay, so that must mean that the normal component of the velocity does contribute to the mass flow through our surface. Okay, so but the normal component Vn is going through the surface. Okay, so the normal component of this little fluid of the normal velocity component of this little sort of blob of fluid is going through the surface. So it is being carried through the surface. Okay, and along with that velocity, it's carrying its mass, its enthalpy, entropy, energy, etc. Okay, and then we could say then that m dot, based on the normal component of the velocity, is our density times the area times the normal component of the velocity. Well, then we know that the normal component of the velocity is just defined to be v dot n hat. And if we apply v dot n hat, we get this, which is just m dot. So this is a much more formalized expression for m dot through a surface. But now we've implicitly assumed here this is still not fully general, because we have considered what to do if the velocity is not aligned, but we have not considered what to do if there is a variation in the normal component of the velocity along the surface. It could be going fast here, and it could be going slow there. So how do we account for that? So to do that, let's take this result and apply it to a differential patch. Very, very small patch, okay? And this is really the same picture that I had earlier. So we had n hat and the velocity vector v. Okay, and so based on the result that I just showed you, what is the mass flow rate flowing through this small differential patch of area dA? Okay, well, that is delta m dot, which is the mass flow rate that is going through the surface, is equal to rho times v dot n hat, which is just the normal component of the velocity through this small patch, times its area, which is dA. And of course, we are making this patch infinitesimally small, so we can assume that that v dot n hat and rho are all constant on this small little patch. Okay, so we can directly apply our earlier result to find this m dot going through the small differential patch. Okay, so now we know how to deal with a small differential patch. Now how about an entire surface? Okay, well, again, what we do here is what we did for all sorts of things, where we did differential things over a small patch, and we want to find them on an entire surface or volume. You need to add up all the small little differential. So if we consider a pipe here, and we want to find the net, find the net mass flow rate that is going through this area here. Well, we have found what m dot is going through this what m dot is going through that small differential patch. Okay, and so that is just given by delta m dot. And then the total mass flow rate that is going through this entire surface is just adding up all of these super tiny little differential patches, and that is an area integral. Okay, so the total mass flow rate through the surface is m dot is equal to the area integral of all the delta m dots, or if you prefer, a dm dot. Okay, and that is equal to rho times, we just substitute in our result here for dm that we calculated here, and so that's just the area integral of rho times vn times dA, and we use the dot product, and we get the final result that the total mass flow rate through a surface, and the surface can be a goofy arbitrary shape, the velocity need not be aligned with the surface, and the velocity can have a non-uniform distribution. But the mass flow rate through the surface is given by the integral of rho v dot n hat dA over the entire area. Okay. And this works for arbitrary surfaces. Okay, so this is very general. It works for basically everything. And so now what about other flow quantities? Okay, so I talked about that we might want to know the flow of the net flow of energy or enthalpy going through the surface, or even how much fluid momentum is passing through the surface. Okay, so how about the flow of the other quantities? Well, the enthalpy, I'll just show you the result. We will basically justify it a bit later. For the enthalpy, it's given by the area integral of h times rho v dot n hat times dA, because basically enthalpy is transported along with the fluid. That is, if I consider again a small little blob of fluid and I follow it around, this blob of fluid can have attached with it an entropy, an energy, and an enthalpy, and so that is basically being carried along with the mass. Okay. Then I'll say for the entropy, we do the same thing, and that's just the net flow rate, the net entropy flow rate through the surface is just given by the area integral of S times rho v dot n hat times dA, because again, entropy is transported with the fluid. And in general, the net rate at which any variable n or any variable eta is passing through a surface is given by the area, the integral of rho v dot n hat times eta over the area, and I will discuss what eta is later on. And you will be using that quite a bit later on in class. And it's any quantity that is basically moving along with the fluid. Okay. So now you guys may be a little bit confused. Is what on earth does Dr. Hoya mean by transported with the fluid? And what I mean by transported with the fluid is basically any quantity that moves with a fluid particle. So one way to think about this is, if fluids are kind of abstract to you, to me, it always helped me to sort of drill down and sort of think of the actual molecules and what the actual molecules are doing at the molecular level. Okay, so think of a quantity of a molecule. Okay, and so here I have a bunch of little molecules here, and they're sort of flying through space. Okay, and these molecules, they each have a kinetic energy or an energy. They have an internal energy, they have a velocity, and these molecules have their mass. And as these molecules move about, their mass, their internal energy, their kinetic energy, etc., are basically moving along with these molecules, right? As I argued earlier, you can find the density of a fluid or any material really by defining a big enough volume and adding up the mass of all the mass of every single molecule. If you have enough fingers, I don't have 10 to the 23rd fingers, but you can add up the mass of basically all the molecules and divide by the volume. Well, you can do the same thing for a molecule, and you can do the same thing for basically any other quantity, not just the density. And so these molecules, as they move about, are carrying their mass, momentum, energy, entropy, etc. Okay? And so what we can show is that if we think about this at the molecular level, is that that if we consider a small differential patch here, and now we don't have a continuous fluid, but we have a flow where we are actually drilling down and visualizing all the individual molecules, is that dm dot equal to basically rho v dot n hat dA. This is actually equivalent to basically counting up all of the mass of each and every molecule that basically passes through the surface in time delta t, and dividing by that delta t. Okay, and so I will do that actually. Okay, and so if we want to find the mass of all the molecules that basically pass through the surface in a time delta t, we can find that the net flow rate of the net mass of the molecules that are passing through the surface is equal to the sum of the mass of every single molecule that passes through the surface in time delta t, divided by delta t, and you take the limit as the time goes to 0. Okay? Because again, we are interested in the flow rate, not the total number. Okay, and this mass is the mass of the ith molecule that is passed through the surface. Okay, And we can sort of simplify this, is that if we just, since I'm being very hand wavy here, and I guess this is the, and this is the, and again, this is the mass of all the molecules that pass through the surface in time delta t. And if we simplify this, you can think about if the mass of each molecule is the same, then the sum of the mass of all the molecules in time delta t is just the number of molecules that have passed through the surface. So we can just count them up times their mass. Okay? So again, n pass is just the number of molecules that have passed through this fictitious surface here in time delta t. So we know the mass of each molecule. You can sort of look that up. But something would be, how do we find the number of molecules that have passed through the surface in time delta t? Again, we could go through and count every molecule. Well, that's not really practical. So what is n pass? Well, first let's consider a volume of. So let's just consider a small volume of all the potential molecules that can pass through the surface in time delta t. Okay. So I'm going to redraw the pipe here. So here we have a pipe here. This is our small surface dA, and we are going to advance the flow for time delta t, and we're going to count up the number of molecules that are basically passing through the surface. And so the average normal component of the velocity of each molecule, I'm just going to define to be Vn. Okay. So, and this area here in orange is dA. So we want to find the number of molecules that have basically passed through this surface. So first of all, let's just consider how far a molecule can travel on average in this x direction in time delta t. Okay, well, on average, the distance a molecule can travel in time delta t would be the average normal component of the velocity times delta t. Okay, and so that is given by this length here. So basically any molecule that is between here and here will pass through this surface in time delta t. Okay? Any surface that is behind this will basically not pass through the surface in time delta t. It'll make it to maybe here. And this molecule over here will move on average the same distance, and that will make it maybe to here. And this molecule will make it to here. And in the green region, this molecule will basically pass through. Okay? And so if we want to just add up, so we could determine the number of molecules that can pass through the surface, one, by standing on the surface and then basically counting all the molecules that pass through the surface. That's not really practical. Or we could consider or we could just consider all of the molecules that could potentially pass through the surface. And that is all of the molecules that are basically in this green volume here. And now what is the volume of this green volume? That is just equal to the average distance that a molecule moves in the normal direction in time delta t, so that's Vn delta t, times the cross-sectional area, which is dA. Okay? Now we know this, so now we know that all the molecules that can pass through the surface must be contained within this volume here. If they are outside of this volume, they will not be passing through the surface. So now how do we find out how many, so now we know the volume, how do we find out the number of molecules? Well, you guys may have dealt with in your physics classes a quantity called the number density. And the number density is just and this is ND, which is the number density of the molecules, and that is the number of molecules per unit volume. Okay, so if I have a number density of 10 to the 6, that means I have a number density of 10 to the 6 per cubic meter. That means I have 1 million molecules on average in 1 cubic meter of volume. Okay, so the number of molecules in this volume is just the number density times the volume. And since the green volume is basically representative of all the molecules that can pass through the surface, so basically the number of molecules that have passed through the surface in time delta t is just given by the number of molecules that are in this volume. Okay, and that is given by n pass, which is the number of molecules that can pass through the surface, is just the number density of the molecules in this green region times the volume of that green region, and that equals the number density times that volume, which is just which is equal to the distance that they travel to the right times the cross-sectional area. Okay, so now we know n pass. So now we can take that and stuff that back into the number to the mass of all the molecules that are passing through the surface in time delta t. Okay, so this is just the mass of all the molecules passing through the surface in time delta t. So that's just the mass of each molecule times the number density times dA times v in delta t. And so this parameter here is just n pass. Okay, and now I will make a little aside here and note that the quantity m times md are the mass of each molecule. The mass of each molecule m times the number of molecules per unit volume equals a mass per unit volume, which is just the density. Okay, so this parameter here is just rho. So now you're seeing a normal component of the velocity, a delta t, an a, and a rho. So you can see we're actually starting to get close to the formula the formula that I scribbled on the iPad earlier. Okay, so now let's stick this back into our formula for m dot. So then, if we take the limit as delta t approaches 0 of 1 over delta t times the mass of all the molecules that pass through the surface in time delta t, well, that is equal to basically 1 over delta t times rho dA times the normal component of the velocity times delta t. It's just basically this divided by delta t. And we have a delta t divided by delta t. And that is equal to rho times dA times the normal component of the velocity. And we know that the normal component of the velocity is just given by v dot n hat. Okay. So now we have basically proven that, I'm going to say that dm dot, we have basically proven that dm dot equals rho v dot n hat dA by just considering all the potential molecules that can basically pass through this surface in time delta t. Okay, so we have basically, it it is a very hand-wavy argument, but it does work. Then m dot, so then this expression here is just equal to rho v dot n hat dA, and again m dot is just the area integral of that, and so that's basically what we have here. So we can just, so you can sort of, if you think about this at the molecular level and you start counting up molecules, you basically wind up in the exact same sort of a position. Okay, and so that's basically where these formulas come from. The books normally don't show this sort of hand-wavy derivation that I did, but I think it's sort of helpful to know where all these equations come from. They don't just come out of thin air; they are very well thought out. Okay, now that was for mass. Now, what about momentum? Because a molecule also has momentum associated with it. So we could do the same thing, but instead of counting up the mass of all the molecules that pass through the surface, we could count up the momentum of all the molecules that pass through the surface. And so we could basically just do the same thing, but instead of summing up the mass of all the molecules, we could sum up the momentum of all the molecules. Okay, and so this is the momentum of all the molecules. And then we could sum them up, and well, what is momentum? Well, momentum is nothing more than mass times, basically mass times the velocity. Okay, where vi is the velocity of molecule I, and again, this is the sum over all the molecules that are passing through the surface in time delta t. Okay, and notice that we have velocity that is multiplying the mass of the molecule. And so basically this is telling us that when that you could go through this entire argument again here all over, but instead of counting up the mass, you would count mass times the velocity vector. And you would wind up with the exact same result, except for it's multiplied by the velocity. Okay? So then this implies that if we are to find the flow of momentum, we do the same thing. We take the limit as delta t approaches 0 of 1 over delta t times the total momentum of the molecules that pass through our fictitious surface in time delta t. And if you notice that you would go through the exact same procedure, you would just, wherever you see m, you would multiply that by v. And that result, I'm not going to go through it, that basically carries over all the way to the final end. So the final answer then is just that the flow rate of momentum through a surface is just given by the area integral of v, rho v dot n hat dA. Okay? And then if we think back to our general form where we had the flow rate of sum of basically any quantities given by eta, rho v dot n hat dA, and we compare this formula here to this formula here, oops, I got to put the area here, and we compare this formula here to this formula here, we see that eta, in the case of momentum, is just equal to the fluid velocity. Okay? So that's for momentum. And then you can do the exact same thing for the energy. Okay, and again, energy is just given by the mass of each molecule times its internal energy. It's really the kinetic energy. But then you basically do the same thing. You sum it over all the molecules. It will be the sum of all the mass times the internal energy. And notice that you have E multiplying mass. And I'm gonna skip to the very end. But essentially, the flow rate of energy through the surface which is this expression here, is just given by the area integral of E times rho v dot n hat dA. Okay? And this implies that if you use this sort of very generic formula here, and you look that where basically eta is, we have the internal energy E. And so eta is equal to the internal energy of the molecule. I know in your thermo you are used to using U, but we have U for the fluid velocity traditionally in fluid mechanics. So in fluids, in gas dynamics and things like that, it is very common to use E for internal energy, not little u. That's to avoid confusion with the x component of the fluid velocity vector. Okay. It's a shame that fluids and thermo were developed independently. Otherwise, if they were developed together, they could have used a more consistent nomenclature, not recycled a crazy number of variables that are used in the same context. Okay, but now we can sort of see a pattern here that if there is a quantity that is being carried with the fluid, then its net flow rate, or the net flow rate of that quantity through our arbitrary surface, is just given by the area integral of that quantity times rho v dot n hat dA. Okay, and you could sort of see that basically many properties of a molecule are given by that quantity is equal to mass times that quantity per unit mass of the molecule. Okay, or the total amount of that quantity, I'm going to call that cap n, is just equal to mass times r eta. And then we can make a little table for the things that we found thus far. And I'm not going to go through the entire table, but say if n is mass, that's given by small m, eta in our formula is just 1. Again, remember that the flow rate would be A eta rho v dot n hat dA. Okay, so if you want to find the mass flow rate through a given surface, you can apply this formula here. And if you want mass, you use eta equal to 1. Okay, if you want momentum, well, that's given by mass times the velocity. So we are taking m times the velocity, which is right there. And so basically eta would be the velocity. Then you got energy, E, etc. And we can go through the whole table, and you'll be using this more often than you like as we move forward in chapter 4. Okay, so we'll be using this a lot. Okay, and so you'll be using these types of integrals for probably about a month and a half in the class. Okay, so you're going to have to get used to this. Now, there's a very common assumption, and that's called the uniform flow assumption. Okay, and what do I mean by that? And you guys use this all the time in thermo. And that is, for a surface, uniform flow is when v dot n hat, v, e, rho, etc. are not a function of space on that surface. Okay, so I could just draw a picture here of a case where we have uniform flow, and I have our fictitious surface where we're going to find m dot, or the flow of energy through it. And if the flow is uniform, then the velocity profile is perfectly uniform over that surface. It's the same at all points. But, and so you guys basically dealt with that case all the time in thermo. And just now in fluids, we are formalizing it, because in fluids, we have to deal with non-uniform flow quite often. Okay, and a practical example, and we'll be dealing with that a lot when we get to chapter 8, which is pipe flow, is that you could have the flow in a pipe. Well, in a pipe, there is a flow rate that can be going through the pipe, But you learned back in chapter 2 that there's a no slip condition. So the fluid sticks to the wall. So that means that the flow velocity at the wall is 0 on both sides, but there's still a net flow. So that means there has to be some velocity profile in that pipe. Okay, so the fluid is moving faster here than it is moving over here, and so that is a non-uniform flow configuration. However, if the uniform flow approximation is valid, n v dot n hat is also constant, then we can look at our flow rate, our generic flow rate formula, which is this the area integral of eta rho v dot n hat dA. Well, these, since they are not a function of space on the surface, again, we are assuming uniform flow. I'm going to double underline and highlight that so that you don't use this as a generic formula. Okay, if these are constant, you can basically pull them out of the integral like I've drawn here. Okay, and then I can reduce that. And so what I have here, this is just eta times rho v dot n hat times the area integral of dA. Well, the area integral of dA is just the area, and v dot n hat is just vn. And then we can basically simplify this using these two results here, and we get that this whole thing is just eta times v times vn times the area, and this should be essentially the same as what you used in thermo to find the flow rate of enthalpy or m dot or something like that. So this here could be like m dot h. If you're finding the flow rate of enthalpy through a surface assuming uniform flow. Okay, if the flow is non-uniform, then you have to use this. Okay, you must use that. Okay, you cannot, and then in your homework, I expect you to show this every single time. So that is, if you're finding the flow rate through a surface, I want you to start from the generic definition. You can, if you're finding m dot, you don't need to show what eta is. You can just say rho v dot n hat. But I expect you to basically say, look, these terms are constant. I can pull them out. If I pull them out, then I get eta times rho v dot n hat times the integral over area dA. And then I want you to show how you went from here to here every single time. And yes, it's a lot of work. And yes, you're probably going to not like me very much. But again, it's that sort of, it's just getting used to that, is that to be able to go from here to here, you're making a lot of assumptions. And you need to be, as you move forward in your professional careers, you'll be dealing with very complicated scenarios where those assumptions are not valid. And so if all you do is sort of remember these remember formulas for these simple cases, you will not be well equipped to handle the more complex cases that you will encounter in industry, where you are required to use the more generic expressions. Okay? So again, do not just skip from here to here. Okay, now there's a concept. It's called the volumetric flow rate. I mentioned it a little bit earlier. And that is given by V dot or Q. And essentially, the volumetric flow rate is not the mass of the fluid crossing through a surface. It is the volume. It is the volume of fluid flowing through a surface, and it is given by in terms of volume over time. It's given by basically meters cubed. It is given by meters cubed per second in MKS, or cubic feet per second in English, or maybe gallons per minute in everyday life. So if you talk about gallons per minute of your car engine, or you filling a pool or a bucket of water, that is a volumetric flow rate. Okay, and basically you can derive an expression for the volumetric flow rate the same way we did for mass, by basically considering a fictitious surface and considering the volume of all the molecules that are passing through the surface. Okay, and that will give you the volumetric flow rate. And it's very, very hand wavy, but the volume of a molecule, again, extremely hand wavy, but the sort of quote unquote volume, and I'm making air quotations that you can't see me making, but the volume of a molecule is just the mass of a molecule divided by its density. Okay, and so essentially, if we are to use our sort of counting strategy that we did before, what we would have is that the volume passing through the surface in time delta t is given by the sum of the mass of all the molecules divided by their density. Okay, and so this is the rate of molecule volume passing through the surface. Okay, and we can then basically use the exact same result that we did before, and just notice that our mass is multiplied by basically 1 over the density. Okay, and so we find that V dot, or the volumetric flow rate, these are equivalent. V dot or Q is equal to the limit as delta t approaches 0 of 1 over delta t over the sum of the mass of all the molecules divided by the density. And this is the same thing as before. And you can see that we are dividing by density, so you can use the exact same formula that we had before with eta equal to 1 over rho. And so we can sort of work through it some more. And so the volume of all, so the rate of volume of each molecule passing through the surface is equivalent to the area integral of eta times rho v dot n hat times dA, and eta is just 1 over rho. And if I substitute in rho here, or if I substitute in 1 divided by rho, I have rho over rho. Those go away, and the volumetric flow rate is just equal to the area integral of rho, or of v dot n hat times dA. Okay, and that is the volumetric flow rate. Okay, and we will be dealing with that a lot in this class.